Okay, so hello everyone. This is Luboš Pirkl from CFD Support. I would like to welcome you to the webinar where we would like to show you a complex workflow about how to optimize a centrifugal pump. We did this case study here at CFD Support together with CFturbo in Germany. And yeah, we would like to show you how our great software pieces of engineering design software, CFturbo, and engineering simulation environment, TCAE, how they joined their forces to create a complex workflow, how to design and how to simulate and optimize a centrifugal pump. So I'll think we can start. So the webinar is being recorded and the recording will be made later publicly available. And yeah, I think we can start. So I will start with the webinar speakers. So it would be me. My current job at CFD Support is telling the world about us. Together with us is my colleague Radek Máca, who is our head engineer and senior developer, and he will take care of technical issues in today's webinar. So let's ask him if he is ready. So Radek, hello, can you hear us?
Hello, I can hear you, and I hope there will be no technical issues during this webinar.
Yes, thank you. We also hope everything will be okay. We are running live, so sometimes something happens, but hopefully it will be okay today. And yeah, and finally, the best for last, it will be our colleague in Dresden, Oliver Felde is senior scientist and principal developer of CFturbo software. So, Oliver, can you hear us?
I can. Hello, Luboš, hello, Radek, and hello to the audience. It's a pleasure to be here today again.
Okay, great. So it seems we are ready, and I think we can go ahead. And I think we can quickly jump into it. So here is the agenda. After this quick introduction, there will be three parts, I would say. There will be the design part, the CFturbo part, where Oliver will show us CFturbo software and how such a pump is created, how it's born, and how it gets ready to be optimized. And in the second part, there will be the simulation part where Radek will show how to make the connection between these software pieces and how to simulate the workflow and tell us what are the results. And as usual, at the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions, and we will do our best to answer them. The most relevant questions will be answered right away in the webinar, and those which are for example specific and not so much representative, they will be surely answered later via email. So you can be sure that all the questions will be answered. So feel free to ask your questions anytime during the webinar. There is I'm sure you will find a menu question form where you can ask your questions. Okay, so that's the agenda, and I think we can start right away with the design part, where Oliver will tell us how the pump is born and how it's created.
Okay, let's. Can you see my screen now?
Yes, we can. The stage is yours.
All right. Okay, very good. I'm not going to go into greater detail in the design. Rather, I will use a standard example that we ship with the software. But nevertheless, you are welcome to watch our previous webinar available on YouTube, where the design process is shown in greater detail. As I said, we ship a couple of standard example with the software, and they can be found in the appropriate directories. This example we look at today is one of our pump examples, and it's called CP-NQ20 because it's a specific speed of 20 pump design. It's a centrifugal pump, and a special geometric feature is that one can trim this pump and bring it down to smaller impeller diameters, and therefore is able to develop from one reference design of the impeller, for instance, a set of different designs for different operating points. If I open that, I will quickly show a couple of key features of that pump. So the design point is given here, flow rate 60 cubic meter per hour, head 50 meter, and revolutions 2,900 RPM. That gives a specific speed of 20, and it's clear that this is or should certainly be realized as a pure radial or centrifugal pump. Otherwise, the efficiency would not be as good as with this meridional contour. Only very quickly some of the key features of that model. So we have not only the fluid guiding parts designed in that model, but also the solid part of the impeller itself. So the hub and the shroud, they have a certain thickness. There is the casing, and even a very simple sealing incorporated into that design. So if I, for instance, open the second design step, then on the first tab, we have the representation of hub and shroud by Bezier curves. There is the leading edge given as a straight line at a constant radius. The second tab holds the definition of hub and shroud contour. So here we can almost design almost anything what is rotationally constant, because points can be introduced by right click on the curves and split the curves. Bezier points can be added. There can be radius defined. All things that are necessary for the design. And the second tab, or the last tab, will hold the definition of the what we call the secondary flow path, and that's just something that closes the volume, the fluid volume, and is very important in CFD, because only if that secondary flow path is well defined, then one can really simulate the behavior as close to reality as possible. Because otherwise, if this was not included in the simulation, the leakage flow, for instance, that would occur between outlet of the impeller and the suction mouth at the shroud, that would be otherwise not be considered in the simulation process. The whole model is fully parametric, which means at any time you can change, for instance, numbers of blades. So I change it from 6 to 7. Blade angles change to 23, for instance, or I can change the general blade shape. So I could change it to freeform. 3D could increase the numbers of spans, and then if I press the OK button, there would be an update, and if I do not make it too bad, then the 3D geometry could be generated. I did probably a bit too much. That's why on the right hand side some warnings may occur, but still the 3D geometry would be generated, and that is very the important feature that it is needed for a automatic optimization process. So yeah, I already said there is a labyrinth kind of sealing implemented. There are fillets at hub and shroud, at the blades are implemented. So all the features that you might want to see in a CFturbo model, and because I want to go back to the original state, I make an undo, and then I run what we call the model finishing, because then high quality solids are generated, and the 3D model, for instance, used for CFD application, but also in the CAD interfaces, will have a very high quality. And if I switch to the 3D model view, then I see how the stage is made up here in the 3D view. In the component tree, I can tell that I just want to see material domains only, so which is in this case the impeller. And you see here how we added thickness to hub and shroud, how we modeled parts of the design which later will be used to mount the shaft in, and also you see the fillets at the blades at hub and shroud, which of course also have to be considered in the design process, especially if they get bigger and bigger. Okay, so that's quickly about the model that we see here, but today's webinar topic is the automatic optimization, and one precondition for automatic optimization is that the geometry model is fully parametric. That's what I tried to show you in the last couple of minutes. The other point is that the geometry generator also has to be able to be run from the command line in a batch mode. So what we have implemented to this end is the batch mode menu, in which one can tell what parameters should be controlled by a another control instance that could be, for instance, an optimizing software. So, and for that webinar, we have chosen just a small set of parameters that are part of the parameter set of the radial impeller, and that is, of course, blade angles, because they will influence both the incidence at the leading edge as well as the Euler work to be generated by the impeller. So that's why I'm choosing blade angles at leading and trailing edge, and I can even give him a range here. So if the optimizer, for instance, is able to read this range, he can use that information for specifying the range in which this parameter should be changed. So the blade angles should be optimized, parameters to be optimized. Then the mean line itself, because we want to adjust the blade with a certain goal, and the goal, for instance, can be the improvement of the efficiency. So to this end, I activate the central point of the mean lines, and also the wrap angle can be one parameter, and that is controlled by the trailing edge position of the mean line. So that's 5 parameters, but that's only half of the truth. The other part, of course, is what kind of export shall be done once the parameter change has been done. And in order to specify that, I need to go to the CFD interface list. I have to select the TCFD interface, and also have to tell all the components that I want to export, and I'm of course take into consideration all of the components because I just want to let the CFD simulate the complete stage. Once that is done, I add it to the export interface list, and then I save that as a special batch file. That was not correct. Okay, now let's give it a different name. Okay, and that's the batch file itself. I can close that and can go to where I have saved it to. So the underlined files are the files that have been just created. I quickly want to show the structure of such a CFD batch file. You see here, it's XML code. It gives you a list of the parameters to be changed by an external program, for instance, by an optimizer. So we have the leading edge angle, the trailing edge angle. There is the central mean line point with X and Y coordinates, and there is the trailing edge position, which is the rep angle. Also, there is the export interface given here. What I have to tell also is the directory where I want to export it to, and that's to be given here, and that's it basically. So just to show you how that then would work, I change the leading edge angle from I think it was something like 11 degrees or so, or 12 to a higher value, so maybe 10.4, and save it. And what I can do, I can now run the CFturbo from the command line, but I can also double click on that CFD batch file. Then CFturbo is fired up. It will read that batch file. In the batch file, there was the reference geometry file given. And if I now open the blade properties, you see that the blade angle has been changed from the reference or the original 11 something degrees to almost 14 degrees. And this can be done by the optimizer, and it doesn't have to be like I did here with the GUI version of CFturbo. It can be also done on the basis of or on the command line without opening the GUI. And I have prepared a little batch file, which is a very simple one. If I open that, you see here, it's just the CFturbo exit that has been specified. It will run in batch mode, and it will take the batch file, either the one that I just defined or a previous one. And that brings me almost to the end. So I fire this up. CFturbo is loading the reference geometry, is changing, for instance, the blade angle, is generating the 3D geometry, and finally it starts to create the geometry data needed by TCFD, and then it will write out all the necessary data. So that triangulation will take a bit of time because we have a couple of geometric feature which makes the triangulation a bit lengthy. But nevertheless, you see here the TCFD file has been created, which holds all the necessary settings for meshing and for the at least design point run in CFD, and also the resources geometry as the resource directory is generated, and that now is going to be filled with the STL data, which are a result of the triangulation process. One thing I have forgotten, that's why I go back to CFturbo, is to tell you what were the other parameters that will be changed in the optimization process. So one was the location of that inner Bezier point of the camber line representation of the blade. So this will be controlled by the optimizer, and the other one is the trailing edge position, which will change the wrap angle, which is also given here in the table in the design process. So in the end, these 5 parameters will be controlled by the optimizer, and we will see what kind of improvement concerning the efficiency one can reach. Of course, maybe a last sentence on that example here. This is an example that has been one of our standard example for a couple of years now. So it went through a well, at least improvement process. So it's already quite a good design, and it's also a low specific speed design with secondary flow paths and so on, which means the efficiency already is quite good, and yeah, we will see how far an improvement process and automatic optimization progress can bring us. Okay, so by doing still the STL generation is running, I would say that was all what I wanted to tell you for the time being, and so I will give back the moderatorship to Lubasz.
Okay, thank you, Oliver, for your contribution. It was very interesting to see how a pump is born from the median view to the 3D model, and how it's completely parameterized. Thank you for it, and we will continue in the webinar. So this was the design part in CFturbo, and now we are slowly getting to the simulation part. Okay, I'm not gonna torture you with too much information. I guess you know it anyway. I'll only mention that CFD Support is a company located in Prague, Czech Republic, and we deal with simulations. Especially we deal with specifically with CFD, FEA, and optimization. Our large advantage, our large competitive advantage is we are dealing with open source integration. We mastered the process of open source integration into like professional CFD tools for the industry, and that's what we deal with. We currently use like our software is based on 49 open source packages, and on top of that, we've spent more than 30 years in team development of them to make them available for the industry, what open source unfortunately is not capable. Okay, so yeah, there's the simulation environment called TCAE we develop, and from the latest release in September 2021, it's capable of optimization, and we would like to show you how to join it or to connect it with CFturbo. So I'll skip all these slides. Maybe I will stop here for a second. It explains why we are so into the optimization. We believe that the optimization is a real big shift in the field. We believe it's a paradigm shift, a shift from the trial and error method to the conceptual search for the best possible. So we believe it's a really big thing, and it changes the world of simulations, in our opinion, because we believe that the world, we're engineers, and we believe the world consists of parameters, and every simulation and every product has also a lot of parameters, and we definitely, based on these parameters, we can design, and it's a big task for everyone. As you know, a human brain can imagine only 3 or 4 dimensions, but we are definitely speaking about a multi-dimensional problem, which is huge. It's perhaps hundreds of parameters in total in such a workflow and design, and such parametric space is of course extremely large. It's huge to navigate in it with random actions. So it definitely has to be a machine, an algorithm which does the work for us, and that's why we are so excited to do this optimization workflows, because it's we believe it's a really big shift from what has been standard years ago. Okay, so we have such a complex approach to it. So it's normal simulation as you used to know it before, but now it's a little bit more complex with the optimization. So yeah, we already did a couple of studies and projects on optimization, and I think it's time to ask Radek to take over the presentation. So Radek, are you still with us?
Yes, I am. Okay, so if you can see my screen,
Yes, we do.
I will continue in the webinar. So in my part, I will show you how to connect the CFturbo batch interface, let's say, into the TOpt part. So as Oliver, I will not go into much detail about the setting, the simulation or meshing, because we already did in the previous webinar. So I will also refer to some of our previous webinars about the simulation of pumps. So today I will be speaking more or less about the connection. Okay, so what we have at the very beginning. So from Oliver, we have a standard. Let's say we have the CFturbo project file for the pump geometry, and the CFturbo batch file for the optimization, which includes the selected parameters to be optimized, and other important parameters for the optimization, like the export or the original project file. So then, if you remember, if you setting up the TMesh or TCFD simulation, you should have available the STL files. So for, let's say, for very first setup, you should also have all the STL files which Oliver generated at the end of his part. So we will take. So based on these geometry files, we can create the standard TCAE setup. So we can borrow the TCFD export file, use them for setting up the simulation, adjust all the parameters to really get a nice smooth converged results for the particular parametric variation, let's say. And if we are satisfied with the meshing, with the simulation, and with the CFD results, so then we can go for the optimization, because if the simulation somehow set in the wrong way, then it's a nonsense to apply the optimization process. So from the side of CFturbo, we have basically these two files and the generated geometry. So we create kind of structure for which we then design the initial script, we call it, which basically do the work how to connect TOpt run with the CFturbo. Yeah, so additional file, we have this init script I will describe on the next slides. And we have our TCAE configuration file which holds all the setup from the TCAE point of view. Yeah, so for each optimization run, the new geometry variant is generated using the CFturbo batch mode, and basically the script do the communication between the optimizer. So in each optimization run, it gives us the new point in the parametric space. We send it to the CFturbo basically via this batch script. We run CFturbo, which generates for us the new geometry variants, export the STLs, and then we can run the standard TCAE workflow like running tmesh, TCFD, and post-process the results, and then the optimization loop continues until some convergence is reached. Well, so this is the standard workflow. Yeah, so if there is no TOpt, then first the mesh is generated, then TCFD run, simulate the CFD simulation. Possibly we can also include the solid, the structure analysis of the solid, which is also possible with connection with CFturbo, because CFturbo can also export the solid of the impeller, for example, and then we are done. So in case of TOpt, we are basically, we have a loop of this process, and it depends on which optimization algorithm we use, but basically if the optimization is run, so based on the given algorithm, we got from the optimization algorithm or from the optimization loop, we got each run the new point from the parametric space, and then if we have this point, we can run the loop, and we do it until some convergence is reached, or we did all the simulation which were explicitly preset. So now, if you would like to incorporate some external tool for generating the geometry, so using the initialization script, which is run for each optimization run, we trigger to run the CFturbo batch mode, for which we provide somehow, I will show you, basically just the parameters which has to be used for the new geometry generation. And after it generates, after it exports the STLs, basically the geometry in STL format, it stores them into the same place because it is defined there in the configuration file of the CFturbo or in the project file. So then when it is done, the TCAE loop, let's say, can continue, and it automatically loads the new STLs from the given path. Yeah, so the initialization script takes care of running CFturbo batch script basically. The new point of the parametric space has to be handed, so all the features are ready for it, and we do it via the modification of the initializations. We do it via modification of the CFturbo batch file. So basically, the script fills the new values of the parameters in it, and then we run the CFturbo exe in the batch mode like Oliver did at the end of his part. And CFturbo builds for us the new geometry, and then the tmesh loads this geometry and continue the simulation run continues. Okay, so now let's say short description about the initialization script. So let me switch for the real, let's say, example. So here, this is the working structure at the very beginning. So here we have the script. Here we have the CFturbo part, so the project file and the original batch file. And here in the export, we have the standard export with all the STLs. Yeah, so if I go to my TOpt, which is here. Yeah, so basically in the tmesh, we can see that the path remains the same. So we are in the CFturbo export resources geometry. So anytime the STLs are available, and for each run, CFturbo gives us the new STLs for the new variants, and it can automatically be loaded. So we do not somehow adjust the path to the STLs. So we did in this way. And in the topt, here we have this initialization script, which is run for every optimization run. So here we basically load the script, which I'm going to describe now. Okay, so let's go step by step pretty quickly. So it is written in Python, so you can use any functionality which Python has. So you can load or add any module if you want to somehow treat a very specific interface. So for this case, we need to just load it, just operating system dependent functionality to run external tools like the CFturbo. And here is a module for parsing and creating XML files or XML data, because the batch file from CFturbo is in XML format, so it will make easier for us to adjust the proper values. Then there is some definition of the variables which tell us the path to the CFturbo exe file. So depending on your installation, your variants, you just adjust this path to your installation. Then, because we would like to know and to tell CFturbo where we are on the disk, so we need to have some reference directory. So from the topt, we can load any parameter. So the params variable holds, it's basically the dictionary, the built-in dictionary, which is always available in the script, which can give us each topt or each TCAE parameter, and we can call the value of it. So yeah, so it will return us the string of the base directory for the optimization. And then we also define the CFturbo working directory, because in there we would like to run this batch CFturbo batch mode. So we just refer from this base directory to the CFturbo following our file structure. Yeah, so we keep it this, and we would like to have the reference to the CFturbo file if you run it anywhere. So if we move this file, this project to some different place, we would like to keep it running. So therefore we use this some kind of base directory reference for our optimization. Then, yeah, basically I have described all the parts at the beginning. Then there is a function which is specific for the connection of CFturbo. So this function basically takes the original batch file, then we create a new batch file because we would like to keep the original one, and we send them the parameters which we get from the topt. So it will be described later. So this function reads the CFturbo batch file, it finds and it adjusts all the optimization parameters using this XML3 module in Python, and saves the modified batch file, which is later used for running the CFturbo batch mode to generate the geometry. Okay, so these are basically the basic functions to how to list or the XML data parts. And basically here, because the parameters holds the name of the parameter, it will look for the particular parameters, and if it founds the parameter, it will set the current value. Yeah, because the parameters basically is the list, two-dimensional list. On the first place there is the name of the parameter, on the second place it's the current value, and basically that's all. So then this function is called in this way. So we have the original file, yeah, from CFturbo working directory. It will create a new one, so with the underscore modified, and we will give to this function the current parameters. So at the end, after executing this function, there will be a new file in our hierarchy which is called _modified. All right, so here in this part we basically read the parameters names. So this must be somehow synchronized with CFturbo parameters names, and this name has to be defined in the topt. So I will show you. So basically here in the topt, you will define how many and which parameters you would like to use for the optimization, and basically this name has to correspond to the name of the parameters which was picked for the optimization from CFturbo environment, because then these names can be automatically loaded in the initialization script and can be parsed to the XML file from CFturbo. Yeah, so this is the, let's say, compulsory. This makes the connection easier if you name it properly, which follows the CFturbo names. And for each parameter, it's simply you set a data type. I think we also have described it in the previous webinar for the TCAE release, I guess. And you can set the minimum and maximum values for the optimization. So where the optimizer can vary the values for each parameter. So back to the script. So here into the number of par variable, we load the number of parameters. So we have 5 parameters. So this variable will hold number 5, and we will create an empty list to fill the names and values of the parameters. So here in the for cycle or the for loop, we load all the TOpt parameters which we define in the GUI, because if you look into the configuration file, there's something like these values. So TOpt, label of the parameter, name, and really the name. So this parameter which correspond to this for each label holds the name. Yeah, so the first item in the list for the par, there will be the name of the first parameter, which is, for example, beta 1, and the first and the actual value. So this is changed by the optimizer. So for each optimization run, there is new value which the optimizer decides to set. Yeah, so basically now we have the list of the current parameters to be simulated, and these parameters are sent to the function which adjusts for us the XML file, the batch file for CFturbo. So the last lines of the script basically do the main job. So first there is let's say specific modification. So because in the XML file there is a name of the output file. So if CFturbo triggers the batch file, it will create the new project file with the new parameters. Yeah, so for each run we define a specific name for it. So then after the simulation is done, we have the project file, CFturbo project file, for each variant which was which was simulated. Yeah, so if I go to the disk, here is our simulation which is already done, and if you go to the CFturbo, yeah, we can all the variants which we can then open in CFturbo and check particularly how the design looks like, or how all the parameters were set, or for further reference we have it available. Okay, then we run the function which sets the new parameters and create our modified batch file, and then by this set of commands we'll just jump into the CFturbo working directory, and we will execute the CFturbo exe in the batch mode with this modified file. and minus verbose will give you some additional information. So this is not important. Okay, and so in each run, you can see that it will create a new modified batch file with the current set of the parameters. And after executing the CFturbo batch mode, we get we get the new set of STLs to be simulated. And basically that's all. If it is preset in this way, we can run the optimization and wait for the tons of data, and at the end we get the best we should get the best efficiency point or best design following our definition. And what is the definition in our case? So our optimization function is the efficiency, and we are following three parameters. First one is efficiency, second one is head, and the third one is power. And let's say our accept range, we keep free hands for the optimizer. So our allowed range for the head, which will include into the optimization, is from 50 to 100. As an example, the same holds for power, from 10 kilowatts to 25 kilowatts, let's say, and the efficiency, some meaningful range of the efficiency. And at the end, if the optimization is finished, so we can list all the variants in the GUI which were simulated, and we can also look for the final HTML report which holds all the information about each variant, so the particular values of the parameters and the goal parameters as a result. Here is also the simulation score, which gives you if the simulation went well. So there are some basic parameters if the I don't know, residuals are good, if the flow rate is not oscillating too much at the inlet and at the outlet, and other parameters, which will give you a first sign of the simulation. So there is a big table of all the variants, and at the end we will see also the best point which were simulated and which were picked based on the TOPT definition. So we have run 300 simulations. We would like to do in the maximum, and the absolute tolerance for the efficiency was something like this. So it was 0.05%. Okay. Then there are a lot of plots. So we can plot each goal parameter, safety parameter, or flow parameter for each run. So we can look how the head of efficiency and power goes through across the optimization process. Then we can also also the couples of the of each parameter versus the optimization function. So how each parameter influence the optimization function, and to see some, let's say, dependence. So you can list it in all these graphs, and similarly you can visualize it into the 3-axis graphs. So there is always the couple of parameters with respect to the optimization function. Yeah, so we can analyze the results and see, for example, if it is somehow moved to the edge of the parametric space, and maybe decide to enlarge the space or focus on that particular part of the parametric space. which is a little bit extended for some parameters. Okay, so my voice is a little bit done, and basically I'm almost at the end of my part. So I will let Luboš to conclude it, and then we can move for the questions, for example. So Luboš, can I hand the presentation back to you?
Yes, absolutely. Thank you, Radek, for your contribution. And okay, we can go ahead with the webinar. Okay, let me know when you can see my screen. I think this direction from your computer
okay,
to mine,
I will let you know. Yeah,
a little bit slower. So okay, let me know when it's done.
Okay.
Yeah, maybe I hope things don't look that complicated. It's a lot of parameters and stuff, but you can be sure that anyone who has any experience with simulations gets quickly into it, and after some experience, it's much faster. And remember, this was just an example of setting things up. Once the things are set, the workflow is set, you just use it, and then it's automated, and it's pretty easy. So only little changes and modifications are usually needed when you change the project or include, for example, new parameters or remove some parameters or play with the workflow. So you do it just once. And also, we are always here to support you if there is anything you would like to help with. So no worries.
Definitely. So we can see your yes.
Okay, yes. Perfect. So we can go ahead. Okay, yeah, we have also this like summary of this case study we did. So you can see the final the final optimized impeller, and also the baseline impeller. You can see they're quite similar. You can see that the blades are a little bit longer and maybe a little bit more rounded. It's also, yeah, sure, you can see the baseline parameters, and also you can see the optimized parameters in here. As Radek mentioned, the impeller, it was just the impeller and 5 parameters of this impeller, and the impeller was optimized for the efficiency. We wanted to make it very simple, so we just claimed the efficiency to be the optimization function, and that's what we did. I think at the end it was 250 simulations. Then the convergence stopped, and you can see the basic results. The optimized candidate has a little lower head, but significantly lower power, and by 1.5 better efficiency. So optimization was quite successful. This case study could be even much better, because we didn't explore the whole parametric space even for these 5 candidates. I mean parameters. So we believe it's just a nice and simple example of what can be done. Of course, you can be sure that the optimization function can be much more complicated. You can say, okay, I'm interested in for example, in all candidates where the head is only above 65, and at the same time I want the efficiency which is above 61%, and at the same time I want to have power lower than this and that. So there are many combinations can be used, of course. So this was just a simple case, and I think this would be nearly it. And finally, we are getting to this Q&A session. So we would like to answer some relevant questions from you. So yeah, Oliver and also Radek, feel free to pick some questions you believe would be helpful to answer them right away. And yeah, all the questions, all the resting questions will be answered later. So because I see the first question from Heiko. Hello, Heiko. The question about the Python, is it included in TCAE and is it usable in Windows? Yes, of course. All these scripts are very simple, right? They're not just like Bibles. It's really a few couple of scripts, and they are available, of course, on request. We will, of course, help to anyone who wants to help with it.
And
because
yep. Sorry. And the modules, like for the XML parsing, is implicitly there. Yeah, so you don't need to load manually something. So it is directly runnable in the
sure. The only artificial part is the geometry, is the connection, right? Because the software, they don't know each other, like from the beginning, right? So the connection, it needs to be done, but it's I believe it's clear and simple. Okay, so it's this. Okay. Yeah, Alex is asking what kind of optimizer is used. It's maybe you noticed we always do this DOE at least a little bit, and then we use a method which is standard, or I would say basic. It's called golden search method. So it's generalized for n-dimensional parametric space, and it's called golden search. By the way, we are already working on very or I would say on sophisticated methods, as you can see them in other open source codes. So you can very soon look forward in the next version. I'm pretty sure that in the next version there will be already a couple of other methods to be picked, and some of them will be much more sophisticated with many interpolation functions, etc. So now it's golden search method in this version. Kind of some. Okay. Yeah, Alex again is asking what happens to failed designs during the optimization. Well, I guess the failed simulations are like thrown away. They're not used in the well, if some candidate is out of the limits that are set, then it's not considered. Then it's like then it's left away, left behind. Yeah. Okay. Yeah. This question is a couple of times in various formulations here, so it's been answered. And yeah, anyone can see a question to answer. Is this? Well, okay, maybe, yeah, there are a couple of questions. I have to admit they're pretty long and difficult to read carefully and answer carefully. So let's keep them for an email. So I think maybe it's time to finish the webinar. So yeah, this would be it. We would like to thank you for your attention. I guess it's obvious CFturbo and TCAE are different software pieces, so questions about CFturbo are best to be sent to CFturbo at info@cfturbo.de, and questions regarding the simulation and other stuff is to be sent to us, to CFD support. And yeah, I guess this would be it. Guys, would you like to say anything for?
Yes, I would like to thank the audience that they have taken the time to see that webinar, and also Lubos and Radek to organize it. Thank you and bye-bye.
Very
Yeah, I
well,
would like to.
thank you.
Yeah,
Yep.
okay, sorry. And I would like to also thank you to Oliver for a nice communication to setting up this optimization, and for the audience to attend this webinar. So it was a pleasure to see you here, and we are looking for further discussion or cooperating on your particular goals and projects. So thank you and bye bye.
Okay, thank you everyone. It was a nice time to spend with you. Yeah, feel free to contact us. It's our job and a pleasure to support you. So yeah, let's keep in touch and bye bye for now.